Today, we're looking at a frankly mind-blowing claim from Huawei. The idea that they can rival 2-nanometer chips without the crucial multi-million-dollar machines everyone else in the world uses. The Chinese tech giant was heavily restricted from participating in the global chip supply chain, but they've just announced a radically new way to build processors. If their numbers hold up, they are talking about achieving absolute bleeding-edge performance without the incredibly advanced tools the rest of the industry completely depends on.
So this is the central mystery we're unpacking today. How exactly does an industry giant plan to bypass the absolute most fundamental tool of modern chipmaking to reach the leading edge? Well, they aren't doing it by making transistors smaller in the traditional sense. Instead, they're attempting something that literally nobody in the mainstream chip industry has seriously attempted at this massive scale before. And if it works, it could absolutely change the phone in your pocket forever. Here is our quick roadmap for today. We'll start with the impossible chip claim, move on to the sanctions bottleneck, how they are folding the chip, the massive 1.5 micron leap, the very real heat sandwich problem, and finally, what this means for the future of chips.
Section 1. The impossible chip claim.
To really grasp what Huawei is doing, we first have to understand the massive brick wall the rest of the tech world is slamming into right now. For about 60 years, Moore's Law was the golden rule. You shrink transistors, you cram twice as many onto a chip, and boom, everything gets faster and cheaper. But those easy gains, they're completely gone. I mean, you've got giants like TSMC fighting tooth and nail just for a measly 6% performance bump. Building a bleeding-edge factory today runs around $20 billion. $1 billion just in development for a single generation of transistor design. The era of cheap, easy progress is absolutely over.
Section 2. The sanctions bottleneck. But for Huawei, this bottleneck wasn't just about physics. It was about strict geopolitical constraints. Escalating U.S. restrictions essentially severed Huawei and their manufacturer SMIC from buying the world's most advanced chip-making gear, starting with initial restrictions in 2019 to tighter controls in 2020, and by 2022, total cutoff from the absolute most critical manufacturing systems on the market. And without those massive machines made by a company called ASML, printing the tiny patterns required for modern 3-nanometer and 2-nanometer chips is, well, it's virtually impossible. Just to put this in perspective, these EUV, or extreme ultraviolet lithography machines, cost around $200 million a pop and weigh as much as 2 whole commercial airplanes. They literally use lasers to blast tiny droplets of tin into plasma. It sounds like straight-up science fiction, but it's what makes modern tech run. And Huawei, they can't buy one. So to survive, SMIC had to fall back on older DUV, or deep ultraviolet machines. They used a really clever workaround called multi-patterning. It's kind of like trying to draw a super detailed picture, but you're only allowed to lay down one single color at a time. Breaking the patterns into simpler, separate steps was a genius move, and it got them to a 7-nanometer equivalent. But eventually, you hit a ceiling. Every single extra step adds immense cost, huge complexity, and tons of opportunities for failure. You just can't push old tech forever. Section 3. Folding the chip. Knowing they couldn't just brute force older tools indefinitely, Huawei's engineers asked a totally different question. They realized that transistor size isn't the only way to make chips better. Get this. In modern systems, over 80%, 80% of a chip's energy is completely wasted, just shuttling data back and forth across its internal wires. It's not doing math, it's just commuting. Those tiny metal wires act like narrow pipes, causing a massive traffic jam. So the bottleneck isn't how fast the transistors compute, it's how fast the data can travel between them. So instead of building a sprawling flat 2D city, Huawei introduced something they call tau scaling. They're basically building a 3D skyscraper. They're optimizing for time by essentially folding the chip in half, kind of like a piece of paper. Think about it. If you fold a page, words that were inches apart are suddenly touching, separated only by the thinness of the paper itself. Shrinking that data travel distance from millimeters down to microns cuts out so much delay, energy waste, and heat. The early results they are showing are wild. This stacking method packs 55% more logic into the exact same footprint. We're talking 238 million transistors crammed into a single square millimeter. This is what gives them a roadmap to a 1.4 nanometer equivalent performance by 2031, without ever touching an EUV machine. Now, notice that word equivalent. They aren't magically creating a 1.4 nanometer wide transistor. They are stacking mature, older chip layers to deliver the performance you'd normally expect from a 1.4 nanometer chip. It's a total system level trick, but man, Is it brilliant?
Section 4. The 1.5 micron leap.
Okay, here's where it gets crazy. To make a 3D stack actually function, the two layers have to communicate flawlessly. The current industry standard for connecting stacked chips, like what AMD does, is a 9-micron gap. Huawei is targeting 1.5 microns. That means they are trying to pack 6 times more microscopic copper connections into the exact same tiny area. The smaller those copper dots are and the closer they are spaced, the faster the layers can talk. If Huawei actually achieves 1.5 microns, the seam between the two stacked chips essentially vanishes. They stop acting like two separate chips and just become one unified powerhouse.
Section 5. The heat sandwich problem.
But, there's always a catch. Every engineering miracle comes with one. And for tau scaling, it's a harsh reality check from the laws of thermodynamics. Because Huawei wants to cram this into a smartphone without, giant data center liquid cooling, stacking 2 hot logic chips creates what's essentially a heat sandwich. The inner filling is basically on fire. Unlike memory chips, logic chips switch billions of times a second and run incredibly hot. Stacking them traps the heat from the bottom layer directly under the active top layer. Managing this inside a tiny, thin phone in your hand, that is literally one of the hardest problems in physics right now.
Section 6. The future of chips.
So is this a true roadmap or just a really impressive presentation? It's all going to come down to manufacturing yield over the next few years. Because look, a chip that fails 60% of the time on the assembly line just isn't a viable product. We absolutely need to see if they can actually tame that intense heat inside their future stack smartphone chips. And equally important is how heavyweights like TSMC and Intel are going to react. If Huawei proves that 1.5 micron bonding is easily manufacturable, the whole semiconductor race shifts to a totally new battlefield.
All right, as we wrap up this explainer, I want to leave you with this final thought. Huawei has basically found a highly creative loophole in both the laws of physics and international geopolitics. They looked at chip making completely differently, simply because the traditional path was walled off to them. But will this massive 1.5 micron gamble actually rewrite the semiconductor playbook by 2031? The engineering is absolutely real, the heat problem is terrifyingly immense, and the stakes, they literally couldn't be higher. So, what do you think? Can they actually